So shown here is a flow chart and just a diagram that I wrote up in fourth period today that quickly and efficiently describes all of the major concepts that we discussed in the previous class when we were going through the PowerPoint, and hones in on some of the biggest ideas to make sure that you took away from them, just to ensure that you know what's going on and you're up to date on our information. So the very first thing here is a little bit vague looking, and I've got S versus V, and it was simply because my handwriting is awful on here, but I'm going to try my best. And we're going to say this right here, this S stands for scalar. All right. And then this one right here is vector. So scalar versus vector quantities. Hopefully you remember what the difference is. But a scalar quantity is one that has only magnitude, or just the number. So examples of this would be things like volume, mass, temperature, all that good stuff, things that do not need contextual information such as direction. A vector, however, is generally represented as some kind of an arrow, and you'll see me draw it as a one-sided arrow just because that looks fancier. Also, it's faster. I don't have to come back and draw the second tail. And a vector is a arrow that is going to represent motion in a direction. So motion with a direction. So the motion is generally signified by the length or the quality or the quantity, excuse me. The quantity of that motion or the change in position is generally represented by the length of the arrow. The longer the arrow, the more position change. And then the direction of that arrow is going to signify where that motion is headed. And so in physics, if you guys had a physical science class, you probably just talked about speed and speed limits and everything like that. And that was probably useful. But here we have to really specify what is happening, because as far as physics is concerned, if you look at where this physics is then applied, this communication, this specific communication of direction becomes extremely important. So we're using it in places like navigation and direction. So GPS data, air traffic control, and port authority control, meaning any kind of an official that's going to be working with a headset looking at radar data or tracking data of GPS locations of either some kind of ship, either an airship, also known as an airplane, or a water-based ship coming into some kind of a port, either a literal port in the water if we're talking about boats, or an airport if we're talking about planes. These large, heavy passenger or cargo-laden transportation methods, such as airplanes and boats, are constantly coming in and out of ports, and they need to do so efficiently. If you've ever been near Atlanta, you can see probably 10 to 20 different planes in the sky at any given point, and they are generally flying circles over the city, which means that they are just waiting in line to be able to land. And the communication of where they are, what direction they need to come into the airport, what the wind is doing, how strong the wind vectors are, all of that information has to be able to be recorded, cataloged, and then communicated efficiently in order to make sure accidents don't happen. All right, because these transportation methods are large. They carry important goods, especially if they're carrying people. And they also are generally full of lots of explosives known as fuel. So you don't want any kind of an accident happening. So speed versus velocity is the next big idea here. And that is coming directly from the scalar versus vector dichotomy I've set up here. So speed I've gotten coming straight from the scalar is a scalar value. It is just your change in position over time or distance over time. And it does not take your actual location or starting and final position into account. It's just the amount of distance traveled. And then velocity here is a vector quantity, because velocity, if we see here, is a result of displacement over time. Displacement is a vector. It is your change in position with a specific direction that you've moved. And so because you're putting displacement into the equation to get velocity, velocity as an output is also a vector quantity. So here I've gotten drawn this would be a top-down view So maybe like a Google Maps or Google Earth view of a location where I set the intersection of these as the origin. And then I've got several vectors drawn here. So the big idea here is that if I were to say I'm going to move 5 meters from the origin point here, I've drawn a circle here that is centered on our origin, and I just arbitrarily said that it was 5 meters. So we've got some radius of 5 meters. All right, so I can say, R equals 5 meters. And that radius there is part of that circle. And if I said 5 meters, I've given you a distance, but I have not specified a direction. And so I can technically occupy any space along the circumference of that circle, and we do not know where I am. So it's like, where in the world is Carmen Sandiego? But it is, where in the world did Mr. Sellers end up? So if I want to specify to you that I am going to move 5 meters northeast, I know that that means, or you will know then, that means I ended up in this location right here. So this is the vector of motion, and it very clearly, if you were to measure an angle there, would specify where I ended up. And there's no questions there. All right, and then here I could say 1 meter northwest. I could move due west and go 5 meters. I could go southeast by 4 meters. And all of these statements actually tell you exactly where I ended up, so long as you know where I started. So this is why we set an origin point, which is what this big red dot right there is. This is where I'm originating my motion, and is where all my subsequent motion is going to be measured from. So just be aware that these are coordinate systems, and they are made for specifying your location change, so your position change. All right, so we keep on scrolling. And then here I've got the definition of velocity mathematically stated as the change in displacement over the change in time, remembering that this triangle here is a delta, meaning change. And that triangle actually represents these two values here, or this set of two values of a final position minus an initial position, and a final time minus an initial time. So that allows us to then clarify what section we're actually talking about. So am I talking about the entire length, and then I'd start at the very start and the very end? Am I taking a small section within that? And so this allows for, again, specificity. And then we look at the idea of constant motion. So before I get to that really quickly, I just wanted to point out these are algebraic rewrites of this definition here, where I have solved for displacement by multiplying time onto the other side. And then I've solved for time from this equation by dividing velocity over. And these are the three basic versions of this, and will be as basic as the math gets in this course. And you will use this occasionally. Sometimes you won't need complicated math. It's just going to be a real quick use of this right here. Now this right here is a image of constant motion. And the way I can describe this as constant motion is if we look at our variables, we've got x, or change in position, on the y-axis, and then the change in time on our x-axis. So I've just drawn in some random points. Excuse the scaling. I know it doesn't perfectly line up, but we're going to pretend it does. All right, and so if I draw this line, this represents, if it's a straight line, it is able to be described with the equation y is equal to mx plus b. And in that case, that means that there is a constant slope that is able to be described. The only kind of line where you can have a slope is a linear graph. And that's why it has the word line in it, the first 4 letters. So if you can see a relationship like this, you know that there's going to be some slope, and we can start talking about the fact that that slope is constant. This means that the quality of velocity is not going to change. All right, so if we look, the change in position over the change in time, that would technically be a change in your y value, so that's going to be changed in x, over a change in your time value here. And so that's going to be a change in your y. And you should know that slope is equal to change in y, or y2 minus y1, over change in x, x2 minus x1. So hopefully you remember that from algebra. And that means here that our velocity is equal to the slope of a position versus time graph. So when we have a constant position versus time graph where the line is linear, then we can describe the average as being the instantaneous. So what that means is that any given instant, if I pick any point along this line, the slope at that line is equal to the total slope over the whole thing. I've shown that here just with some numbers. So if we look at our first interval of 5 meters in 10 seconds, that's going to give us a 5 meters per 10 seconds. You divide that out, you get 0.5, and I think the per second's got erased here, 0.5 meters per second. And then if we did the same thing for 10 meters in 20 seconds, which would be the projection of this line to right there, we would find the same ratio. And so even the instantaneous rate there and the instantaneous rate there is the same. And what we notice is that if that's the final position, this is actually the average. And so long as that line is constant, we've got that average is equal to any given instant along the curve. All right, and then here again, you've got the statement that the slope is equal to velocity. Now I've got another curve here, and I want you to pay attention to the red line. So the red line here is actually the one we're paying attention to. So I'm going to erase this really quickly, and I'm going to draw in that line again. So we've got a curve, and this is just a little bit better looking. So this curve right here is not constant. All right, so if you were to be asked what the slope of this line is, you would not be able to give me an accurate answer because the slope is constantly changing. All right, that's part of the definition of curve. And because of this, you are going to have to talk about differences in average and instantaneous slope. So if I were to take the average slope, that is this line right here. You are just simply going to be paying attention to final position and initial position. So I'd take that there, and I'd take this here, and I would subtract those two. I'd find the time marker and my position marker, and I'd use that to find average velocity there. However, that is not going to be fully adequate. So it will give you the information that you would have had to hold an average velocity of a slope of that right there in order to get to that position, and that's not true of any point along this curve. The only point along the curve that holds that velocity is actually halfway between the final and initial position. If we notice, if we were to draw a line of a slope right there, we would actually end up seeing a line that has the same slope. So let me see if I can get that going. So this right here, hopefully you can see, would be parallel with that. And so there's only one point that actually matches the average. And if you know about the average, right, if you take two data values, the average should be halfway between. So this is the only instant or instantaneous speed that matches our average. Any other speed is going to end up causing issues. All right, so let me see if I can do something really quickly. It's not going to let me rotate it, is it? Oh, look at that. Look at that. All right, so now we go a little bit further along, and the slope gets steeper. We go a little bit further along, and the slope gets even steeper. And by the time we get here, the slope's almost vertical. All right, but if we were to pay attention to the slope at the very beginning, we would notice that it's a little bit less steep, and then we keep going further toward the beginning, and we're going to notice that we've got a decreasing slope. And so it seems like the slope is increasing as you go, and we stated that the slope of a position versus time graph is velocity. So that's going to suggest that if you have a curve like this, that means your velocity is, as the slope is, increasing as time goes on. So this would be described as speeding up. All right, so this is speeding up. And you're going to have to do exactly what I'm showing you right here, where you're taking the slope at a tiny interval of time. So just to show you what that looks like, we're going to decrease the font size here because it's a little bit chunky. And I'm going to draw it in with blue. But for instance, if I wanted to take the slope at that point, I'm going to have to look at this interval right there from that time to that time. And then technically from this position to that position. And so I'm going to be looking at this tiny itty bitty section there. And when I do that, that's going to allow me to talk about the slope at that point. And so that means, let me get that a little bit more accurate. Oh, just there. So I'm going to tilt it just a little bit more. Here we go. And so we'd end up getting a slope that looked like that between those 2 points. And those are the 2 points you're going to measure your y2 over y1 over, or y2 minus y1 over x2 minus x1. And so this concept here is called a tangent line, and it's how we are going to determine instantaneous velocity. So this was just a review of all the stuff that you should have gotten out of last class. And then we're going to see 3 graphs. Yes.
For the midpoint thing, could you do that again between the midpoint and the endpoint?
Okay, so just to clarify, on average, the only time your instantaneous velocity will match an average velocity, where you're just drawing that blue line right there, should be halfway between the 2 endpoints. And so if you know anything about an average, you'll know that if we're just taking these two, it'll be that x final plus x initial. Sorry, I missed my plus x initial over 2, right? That's how you would find your average. And so if you were to find the average like that, you would end up finding that it's going to match halfway down that graph if we've got, you know, a traditionally exponential curve here. And so there's only one point on the curve that matches that average, and it will be halfway between the beginning and the end. Any other point on the curve will have a different slope.
If you were to use the midpoint and the endpoint, though, could you find like the 75% point?
Yeah, and so you would end up, now I would caution you on that. This is dependent on that curve being, you know, perfect. And that's not always the case, especially if we're dealing with raw data. But if I were to just really quickly, I'm going to stop recording because that's pretty much all that 7th period needs to know. The only other thing that you would need to know would be we've got 3 graphs, and we'll be learning about, at least non-AP classes, we'll be learning about that last variable graph next week.